In the last video, we saw the law of conservation of momentum applied to solve one-dimensional inelastic collisions. In this video, we will discuss collisions in 2 dimensions. The simplest 2D collision involves an object moving in X colliding with an object moving in Y. An example is this car crash in which, fortunately, no one was seriously hurt. Notice how the 2 cars mostly stick together after the collision, very similar to the 1D collisions from the last video. Consider this puzzle. A 1,000 kilogram car is traveling at 4 meters per second east. A 1,500 kilogram car is moving at 3 meters per second north. They collide and stick. What is their final velocity? In this question, we have a 1,000 kilogram car which is traveling eastwards in this direction at 4 meters per second. We also have a 1,500 kilogram car which is traveling northward at 3 meters per second. These 2 cars are going to collide with each other. Photo 1 is before they collide, so we're now looking at these sort of as a bird's eye view. After the collision takes place, they're going to stick together and move off in some direction like this. So this is going to be photo 2. Photo 2 is after the collision took place. So this is all of the information that we have been given. Let us now provide our origin and axes. In a conservation of momentum question, the origin is usually put at the point of collision. I'm going to set rightwards as my positive x-axis and northwards as my positive y-axis. In general, you don't have to put the axes on both photo 1 and photo 2. I'm just doing that for clarity. In this case, maybe it makes a little bit more sense to do it on photo 1, but really, as long as they're there in one place or the other and they're unambiguous, you're going to be fine. So now, let us put together all of the information that we know. Let's start with conservation of momentum. Conservation of momentum says the total momentum that's there in photo 1 equals the total momentum that's there in photo 2. The total momentum in photo 1 comes from 2 sources. There's the momentum of the 1,000 in photo 1 plus the momentum of the 1,500 in photo 1. And that's got to be equal to momentum of the 1,000 in photo 2 plus the momentum of the 1,500 in photo 2. Now, let's expand this by using the definition of momentum. Momentum is mass times velocity. So the mass of the 1,000 kilogram car times the velocity of the 1,000 kilogram car in photo 1 plus the mass of the 1,500 kilogram car times the velocity of the 1,500 kilogram car in photo 1. I suppose if I really wanted to be really rigorous about it, I'd put the ones in the subscript for the mass as well. It's not really important over here since the masses of the objects aren't changing. But in any event, let's keep going. The mass of the 1,000 in photo 2 times the velocity of the 1,000 in photo 2 plus the mass of the 1,500 in photo 2 times the velocity of the 1,500 in photo 2. Now, let's plug in all the information that we know. The mass of the 1,000 kilogram car is, of course, 1,000 kilograms. The initial velocity is 4 I hat meters per second. Plus, the mass of the 1,500 kilogram car is 1,500 times its velocity is 3, but this is in the y direction, so this is 3j hat, is equal to 1,000 times the velocity of the 1,000 kilogram car in photo 2, which we don't yet know, plus 1,500 times the velocity of the 1,500 kilogram car in photo 2 as well. Now let's start simplifying this. 1,000 times 4 will give us 4,000 I hat, plus 1,500 times 3 gives us 4,500 j hat. Now, we can simplify this right side because the velocity of the 1,000 and the velocity of the 1,500 will be equal to each other because they've stuck together. So we can take these two velocities and factor them out to produce a final velocity out here, which is based on the two masses, 1,000 plus 1,500. So it's sort of like a reverse distribution that we have done here. This left side, importantly, cannot be simplified anymore. You cannot add a component which is in I with a component which is in j to produce, for example, 8,500. The i's and the j's have to stay separate because I is talking about the x direction and j is talking about the y direction. You cannot mix those together. But you can simplify the right side because 1,000 plus 1,500 is going to give you 2,500. And so the last thing to do is to take this entire left side and divide it by this 2,500. So that's going to give us a final velocity of 4,000 divided by 2,500 is going to give us 1.6 I hat, plus 4,500 divided by 2,500 gives us 1.8 j hat. And that would be in meters per second. So we have now solved for the final velocity of this pair of cars after the collision occurs. The final velocity is 1.4 I hat plus 1.8 j hat meters every second. Every second it's traveling 1.6 meters in the x direction and also 1.8 meters in the y direction. The process that we have used for this two-dimensional collision is identical to what we did for the one-dimensional collision. We drew our two photos, we set our axes, we used conservation of momentum, expanded it out for each car, expanded that out further by using the definition of momentum, mass times velocity, substituted in everything we know, and then simplified. The only difference is we had to keep the i's and the j's separate in this two-dimensional case, which we didn't have to do, obviously, in a one-dimensional case since we didn't have i's and j's. Everything was in the same direction. So a two-dimensional case is just a one-dimensional case where we keep the i's and j's separate. And this is how we solve a simple two-dimensional inelastic collision. If the objects are not traveling exactly along the x and y axes, we need to break their motion into components before we can solve. This is very similar to the breakdown we used to do in kinematics and forces. Consider this example. A 5 kilogram asteroid is traveling rightwards at 3 meters per second. A 4 kilogram asteroid is traveling at 2 meters per second at an angle of 45 degrees above the rightward x-axis. The asteroids collide and stick. What is their final velocity? In this case, we have a 5 kilogram asteroid that is moving at 3 meters per second in the rightward direction. And we also have a 4 kilogram asteroid which is moving at 2 meters per second at an angle of 45 degrees above the horizontal. Now, these two are eventually going to collide with each other. And that collision is going to produce this joint body over here, and that will go off in its own direction. So photo 1 is going to correspond to before the collision, and photo 2 is going to correspond to after the collision. Now I'm going to set the origin and axes on the 4 kilogram object, and here's the reason why. It'll make it easy for us to take this vector of velocity, which is 2 meters per second at an angle of 45 degrees, and to convert it into its Cartesian equivalent, its rectangular equivalent. This is right now in polar notation. We need to turn it into Cartesian before we can start solving for the final velocity, or even the initial velocity of the 4 kilogram. Now, you'll notice that I have now drawn these axes over here. Although it's more conventional to draw them at the point of the collision, which I've marked with this asterisk over here, it doesn't particularly matter as long as you stay consistent and you don't confuse the I-hats and the J-hats. So let's go ahead and let us break this into its components. This over here is the opposite side. The Y component is the opposite side of this right triangle. So this is going to become 2 times the sine of 45 degrees. Length of the hypotenuse, that's r, multiplied by the sine of this angle. We can check this out. This will be 2 sine 45 is 1.414. So the J component of the motion of this asteroid is 1.414 J hat. What about the horizontal component? That would be 2 cos 45 degrees, because this component is adjacent to the 45 degree angle. That's 1.414 I hat, because when we work it out, we're going to find that 2 cos 45 degrees gives us actually 1.414, the same thing. Sine and cosine are the same for 45 degrees. Sine 45 is the same as cosine 45. So now that we have all this information, let us put it all together and let us apply conservation of momentum to find what the final velocity would be. The total velocity before the collision must equal the total velocity after the collision. So P1 is the total velocity in the total momentum in photo 1. P2 is the total momentum in photo 2. So P1 would be the momentum of the 5 kilogram object in photo 1 plus the momentum of the 4 kilogram object in photo 1 is equal to the momentum of the 5 kilogram object in photo 2 plus the momentum of the 4 kilogram object in photo 2. Let's expand this out further. The mass of the 5 kilogram object in photo 1 times the velocity of the 5 kilogram object in photo 1 plus the mass of the 4 kilogram object in photo 1 times the velocity of the 4 kilogram object in photo 1 is all equal to mass of 5 in photo 2 times velocity of 5 in photo 2 plus mass of 4 in photo 2 times velocity of 4 in photo 2. Now, let's throw in all of the information that we know. The mass of the 5 kilogram is, of course, 5, and its velocity is 3 in the x direction. That would be 3 I hat. Plus, the mass of the 4 is 4, and its velocity is 1.414 I hat plus 1.414 J hat. We have to account for both of these components. And all of that is equal to mass of the 5 times the unknown velocity of the 5 kilogram after the collision plus mass of the 4 times the unknown velocity of the 4 after the collision. Let us simplify the left side. This now becomes 15I hat plus 4 multiplied by 1.414 is 5.656. So that's going to give us 5.656 I hat plus 5.656 j hat. And all of that's equal to, the thing to remember is that these two have the same velocity. So that means that these two velocity terms are the same and they can be factored out. We can write it as v final multiplied by 5 plus 4. Simplifying still further, 15I plus 5.656 I hat is going to give us 20.656 I hat plus 5.656 j hat. And that's going to be equal to the final velocity times 9. Finally, we just need to divide both sides by 9 to find out what that final velocity is. So 20.656 divided by 9 gives us 2.295. Let's call that 2.3. Or let's even stick to 2.295. I hat plus 5.656 divided by 9 gives us 0.628. J hat. So this is the final velocity of the two asteroids after the collision occurs. Explosions can be solved in 2 dimensions as well. Consider this example. An object of unknown mass is moving east at 0.86 meters per second. It explodes into 3 fragments. One fragment has a mass of 1 kilogram and travels east at 4 meters per second. The second fragment has a mass of 2 kilograms and travels north at 1.5 meters per second. The third fragment's velocity is 0.5 I hat minus 0.75 j hat. What is the mass of the third fragment? In this question, we have an object of unknown mass which is initially traveling rightwards. So we are first examining it before the explosion takes place. The velocity of this object is 0.86 meters per second rightwards, and this corresponds to our photo 1. Then there is an explosion. Out of this explosion there come 3 fragments. There is a 1 kilogram fragment that travels rightwards at a velocity of 4 meters per second. There is a 2 kilogram fragment that travels upwards at 1.5 meters per second. And there's a third fragment of unknown mass that travels down and to an angle. The velocity, however, of this third and unknown mass is 0.5 I hat minus 0.75 j hat. So this over here, this diagram corresponds to photo 2. We are now ready to set our axes. I'm going to set the upward direction to be y and the rightward direction to be positive x. As usual, we usually put our axes on photo 2. It's not really necessary to choose between photo 1 and photo 2 as long as you're consistent. But here we can clearly see the point of the explosion, which is usually where you set your origin, and the directions that the 3 scattering objects travel in. So we could additionally draw it over here. Again, you don't have to draw it twice. just make sure that it is unambiguous between the two pictures. Now, we are ready to apply conservation of momentum. The total momentum in photo 1 is equal to the total momentum in photo 2. The total momentum in photo 1 comes from this unknown mass, and the total momentum from photo 2 comes from the 1 kilogram, the 2 kilogram, and this unknown mass over here, and all of their respective velocities. I'm going to do something a bit different. I'm going to solve out for the right side of this equation first. In the right side, we have the momentum of the 1 kilogram object in photo 2 plus the momentum of the 2 kilogram object in photo 2 plus the momentum of the unknown mass object in photo 2. I'm going to call this P sub u. If I were to expand all this out, that gives us mass of 1 in the second photo times velocity of 1 in the second photo plus mass of 2 in the second photo times velocity of 2 in the second photo plus the unknown mass in the second photo plus times the velocity of the unknown mass in that second photo. Now, I'm going to go one step further. I'm going to substitute in all of the known information into this right side. That's going to give me mass 1, velocity 4I hat for this first fragment, plus mass of the second fragment is 2, plus velocity of the second fragment is 1.5 j hat, plus the unknown mass, I'm just going to call that mu sub 2, multiplied by the velocity over here, which is 0.5 I hat minus 0.75 j hat. Okay, now I got to all of this step without actually solving anything on the left side. And here's the reason why. When I expand out this left side, I want to be able to account for what the mass is going to be. Now, across these three fragments, we know that there's a 1 kilogram fragment, a 2 kilogram fragment, and the unknown fragment. So the total mass on the right side is 1 plus 2 plus unknown, or 3 plus unknown. Since this left side is going to be equal to mass times velocity of this object over here, that is going to be written as 3 plus this unknown mass multiplied by the velocity on the left side, which was 0.86 I hat. So the velocity of the combined object, so maybe we could call it v sub c for combined object, in photo 1 gets multiplied by the mass of the combined object in photo 1. And we could call this the momentum of the combined object in photo 1. So, what does this mean? Let's pause for a second before we continue our calculation. We have this combined object here, which has an unknown mass. We do know that that unknown mass is going to be more than 3 kilograms, since 2 of these fragments add up to 3 kilograms, and the third one is unknown. But we don't know how big this is. We are going to call this 3 plus the mass of the unknown thing, so that we can use the same mass of the unknown in both sides. The velocity of the combined object is 0.86 I hat. So now we have filled in what has happened on the left side. We started with conservation of momentum. We expanded it out to all terms, the combined object on the left side plus the 3 objects on the right side. Then we expanded it further to account for the definition of momentum, mass times velocity, for each one of these terms. So now, the next thing to do is to start simplifying all of this. And if we're lucky, we should be able to isolate the unknown mass. Now, 3 times 0.86. Let us solve that out. That gives us 2.58. So when I multiply all of this out, I'm going to get 2.58 plus 0.86 mass of the unknown object in photo 1. This is the momentum in the I-hat direction. This is going to work out to 1 times 4 is 4 I-hat, plus 2 times 1.5 is 3 j-hat, plus, now we'll distribute this over here as well. This is going to give us 0.5 times mass of the unknown times 2 at photo 2 I-hat minus 0.75 mass of the unknown at photo 2 j-hat. Now, one thing that I notice over here is that we have a term in I-hat on the left side, but we have no j-hat term on the left side. That means that j-hat on the left side is 0, and that makes sense because this object was moving horizontally. There's only an I-hat term, there's no j-hat term. So let us say that we were to take a look purely at the j-hat terms and see what happens. If I were looking just at the j-hats, the j-hats on the left side are 0, the j-hats on the right side are 3 j-hat minus 0.75 mass of the unknown object in photo 2 times j-hat. So this is going to simplify to 0.75 mass of the unknown in photo 2 j-hat is equal to 3 j-hat. Divide both sides by 0.75 and also by the j-hat, and you get mass of the unknown is equal to 3 divided by 0.75 is 4. A more complicated example is that of scattering. In scattering, two objects bounce off each other instead of sticking, like all the other examples we've seen. Even so, conservation of momentum must still be upheld. Consider this case. A 2 kilogram object is traveling rightward at 5 meters per second. It hits a 10 kilogram object initially at rest. It bounces off at 4 meters per second at an angle of 120 degrees. What is the final velocity of the 10 kilogram object? In this question, we have a 2 kilogram object that is initially moving at 5 meters per second, and a stationary 10 kilogram object, an object which is at rest. Now what's going to happen is the 2 kilogram object is going to bounce off the 10 kilogram object. So if this is the point of collision, the 2 kilogram object gets shot this way, and the 10 kilogram object is going to travel in something like this direction. So photo 1 is before the collision, and photo 2 is after the collision. Photo 1, I will set the axes as follows. I'm going to set the x-axis to be rightwards and the y-axis to be upwards, and I'll do something similar in photo 2. Now, we were told that the velocity of the 2 kilogram object was 4 meters per second at an angle of 120 degrees. That's this angle over here. 4 meters per second at 120 degrees. That is a vector which has been given to us in polar. So we have to convert this into its rectangular equivalent. So, the x component is always given by the length 4 times the cosine of 120. 4 cos 120 is -2. So the x component of this velocity is -2 I hat. And the y component would be for sine 120. That's 3.464. So this would be for sine 120, which is 3.464 j hat. So far, so good. Now, we are ready to apply conservation of momentum. The total momentum for photo 1 is equal to the total momentum in photo 2. The total momentum in photo 1, it comes from two different bodies, the 2 kilogram object and the 10 kilogram object. So the momentum of the 2 kilogram object in photo 1 plus the momentum of the 10 kilogram object in photo 1 is equal to the momentum of the 2 kilogram object in photo 2 plus the momentum of the 10 kilogram object in photo 2. Let's expand this out still further. The mass of the 2 kilogram object in photo 1 times the velocity of the 2 kilogram object in photo 1 plus the mass of the 10 kilogram object in photo 1 times the velocity of the 10 kilogram object in photo 1 is all equal to mass of the 2 kilogram object in photo 2 times velocity of the 2 kilogram object in photo 2 plus the mass of the 10 kilogram object in photo 2 times the velocity of the 10 kilogram object in photo 2. Now, let's plug in all of the information that we know. The mass of the 2 kilogram object is, of course, 2 kilograms. Its initial velocity was 5 meters in the positive x direction, 5 meters per second in the positive x direction, that's 5 I hat. Plus, mass of the 10 kilogram object is 10. Its initial velocity is 0, it is at rest. Is equal to the mass of the 2 kilogram object is still 2 kilograms. Its velocity in photo 2 is -2 I hat plus 3.464 j hat plus the mass of the 10 kilogram object times the velocity of the 10 kilogram object in photo 2, which is what we are looking for in this question. Now, let's simplify everything. 10 times 0 is 0, and 2 times 5 is 10. So this entire momentum on the left side boils down to just 10 I hat, as this term cancels out. Is equal to 2 times -2 is -4 I hat plus 3.464 multiplied by 2 is going to be 6.928 j hat. Plus 10 multiplied by that second velocity of the 10 kilogram object. Now, let us subtract this vector from both sides. So if I were to if I were to add this -4 I hat to both sides, that's going to give me 14 I hat minus 6.928 j hat. So what I've done here is I have taken 10 I hat and added 4 I hat to both sides, and I have subtracted 6.928 j hat from both sides. So that was the step that I did there. It's basically just a subtraction, the only caveat being that I had to keep the I hats and the j hats separate. And all of that must be equal to 10 multiplied by the velocity of the 10 kilogram object in photo 2. So the last step is now to divide both sides by 10, and that gives us the velocity of the 10 kilogram object in photo 2 is 1.4 I hat minus 0.6928 j hat, and this is measured in meters per second. So this is now going to be the velocity of the 10 kilogram object after the collision. In this video, we used conservation of momentum to analyze two-dimensional inelastic collisions and explosions. In the next video, we will integrate conservation of momentum with every previous topic we have seen so far.